All right, it's Mr. Myers with Myers Mathematics, and let's jump into this question. Number 2, it says consider the surface given by f of x comma y, which is z or z, is equal to 36 minus 4x squared minus 9y squared, and the point P, 2 comma negative 1 comma 11, that's on the surface. They were a little generous with the point. They don't have to give you the z. They could just say it's f of 2 comma negative 1. They could have just said that, and then you'd have to find out what the z value is on your own. But they decided to just tell us what it is, so that was nice of them. Part A, and there's more than one part, but I'm just going to do part A so I can keep it a little short. Find the equation of the tangent plane to the surface at the point P. So if you have a surface, and when we say surface, it's some sort of 3D shape, like a ball, right? A sphere. You could graph a sphere, it has an equation, and that equation would involve three variables because we're talking about a 3D shape. So this is a 3D shape. And so just like how a curve, a 2D shape, will have a line, a 1D shape, as its tangent, a 3D shape will have a 2D shape, a plane, as its tangent. So theoretically, if you had a 4D graph, then it should have a 3D tangent plane. But alas, that's a little bit harder to wrap your mind around. We've got a 3D surface, and it's going to have a plane, a 2D piece of paper that is just barely touching the surface at a particular point. It could overlap the 3D shape somewhere else. That's okay. I don't think this one does, but it doesn't matter. It's a local place. So you've got a shape, let's say a sphere, and then at a particular point on that sphere, you'll have a plane. So if I'm looking at it in 2D, it might look like this, but if I'm looking at it a little bit more sideways, that plane might extend out infinitely in every direction, in this direction, in this direction, in the up and down, in every 2D direction that it could be extended out. That plane would just barely touch the ball, the sphere, at the point, and nowhere else, at least immediately around the sphere, which is why it's tangent to it. That's why we call it tangent. All right, so let's jump into the actual math. Um, in order to find the tangent line to a curve, we take the derivative and we set it equal to 0. So we're actually going to do the same thing. Um, However, if we take the derivative right now, when you take the derivative of a function of x, you're taking it with respect to x. We can't really take the derivative with respect to x and y at the same time and have it be meaningful for what we're going for here, which is why we need partial derivatives. That's why we were learning partial derivatives, or you should have learned them already before this. But a partial derivative is when we're pretending like there's only one variable, when in actuality there is more than one. And partials are going to help us out here as well. But we need to know what the partial derivative is for x, y, and z. So we need to treat f of x comma y like it's a z and not like it's something else. So f of x comma y, just like f of x, we call it y. Well, f of x comma y, we can just call that z. So z is equal to 36 minus 4x squared minus 9y squared. So now we could take the derivative, but we're still wanting to take partial derivatives. If we're taking partial derivatives, it might be easier to think of this as x, y, and z all on one side. So we set it equal to 0. So then this would be 36 minus 4x squared minus 9y squared minus z. Now it's almost like we're treating it like it's another function altogether. Some people will go ahead and set it equal to f of x comma y comma z. Like now all of a sudden it's 4D. Um, that's fine if that's what you guys are doing in class, but I find that a little confusing because we're not in 4D. So it's just equal to 0. And when we're taking the derivative, we're taking the partial derivative with respect to either x, y, or z. So I'm going to use different colors to represent the different partials here. We'll use blue for x. So the partial of x will be if I'm pretending like everything else is a constant and only the x is a variable. So the derivative of 36 is going to be 0 no matter which variable I'm pretending is a variable and the other ones are not. 36 is going to go to 0 no matter what. But the negative 4x squared, that's going to be not 0. So I just take the derivative like normal, multiply by the power, negative 4 times 2, and then power minus 1. All right. Then if I'm pretending like y is my only variable, f of y. So 36 still goes to 0. The x would go to 0 as well because it's now a variable, or not a variable, I should say. But for the y, oh, and I forgot to square it. I'm glad I caught that. For the y, it's going to be the derivative of negative 9y squared. So we times the 9 by 2, and the y goes down by a power. And then for the z, I think I'll use like a orange, like a light orange. Yellow's kind of hard to see. So then for the z, the partial derivative with respect to z, same thing. 36 still goes to 0. X and y are now not variables, we decided. And then the derivative of negative 1z. And you could use power rule on this, by the way. Technically, it would work because you'd be timesing 1 by 1, so it'd just be 1. And then you'd be subtracting the power by 1, so it'd be z to the 0 power. And anything to the 0 power is 1. So it's just negative 1 times 1 times 1, which is still negative 1. So that one ends up being negative 1. Okay, so we've got all the partials. And then if you remember, so let's use a different color. I don't know if I want to go back to black though. We'll use a different. We'll use this one. It's like a thing. So if you remember that when you're doing the tangent line to the plane formula, you're basically using point slope form. Point slope, because you're getting an equation of a line. And point slope is a good equation of a line. It's not the only one, but it's probably the best one to use. And that's what it looks like. And you could split up the slope a little bit so that it's kind of distributed into the y and the x. Let's say, for example, y minus 2 is equal to 2/3 x minus 1. So this would mean, in the context of a tangent line to a plane, that we have a tangent line to a plane that has a slope of 2/3, and it intersects the curve at the point 1 comma 2. But could I distribute that slope so that it's evenly distributed to the x and to the y? Yeah, if I times both sides by 3. Now I'm not dealing with fractions. So now the y has a piece of the slope and the x has a piece of the slope. And then I can move it over if I want. And I could set it equal to 0. I could say 0 is equal to 2 x minus 1 minus 3. I'd have to subtract it from both sides, y minus 2. So this is kind of like a weird way to look at point slope form for a line, but this is what you do. This is basically what it looks like for the 3D version, is you need the pieces of the slope, the x piece and the y piece and the z piece all together, because now we're not dealing with just a line, we're dealing with an entire plane. So it's got its own little equation going on. So then if we extend this out into 3D, then what we're basically saying is that we've got 0 equal to the partial derivative of x, so the x piece of the derivative, x minus x naught, or x null, whatever you want to call it. I'm going to put plus. Now, we had to minus it on both sides, but really, I mean, it just depends on how you're viewing the slope. So it doesn't matter that we had to subtract it from both sides. I wouldn't get too caught up in the weeds there. It's just plus, and then y minus the y null, or y naught. And then now we're extending it into 3D. So now it's just fz, z minus z naught. And once we plug it in, we're done. So f of x we've already got. And we need to plug in the value for the point, right? So we're getting equations, but we plug in the values for the points in order to get the actual slope, because we don't want the slope to be, it's going to be a specific slope for the tangent curve, or sorry, the tangent plane to the curve. So we plug in our initial point, which is 2 comma negative 1 comma 11. So specifically for fx, it's going to be negative 8 times x, which is 2. So negative 8 times 2 is negative 16. And then x minus x naught. And that x naught, the x sub 0, that's our initial point. We only know, well, we can find out other points, but we know for sure that it's going to go through that point. So why not just use that point? It's going to go through 2, negative 1, 11. So x minus 2. And then the next part is going to be f of y. Fy is going to be negative 18y, but y is negative 1 for our point. So it's going to be negative 18 times negative 1 is 18. Y minus negative 1, so y plus 1. And then for the z, we're going to do plus, well, actually, it'll be minus, plus negative 1, but minus 1. And then z minus z naught, or the initial point, which is 2 comma negative 1 comma 11, but specifically the 11 is the z value. And then we have our tangent plane to the curve. So I hope that's been helpful. If it has, you can go check out some other helpful things on the channel, or you can go check out my 5 math mistakes everyone makes and how to avoid them. It's a free PDF guide on my website, Myers Mathematics. Go check it out, and I'll catch you in the next one. Blessings, y'all.